Okay, out here recording my video outside my very noisy dance room again. So, L2, hopefully quick video here, just adding on one more concept. So, as we learned in previous lessons, there are angular analogs, as I like to call them, to linear motion that work very similarly. So, we talked about velocity, position, acceleration, angular velocity, angular position, angular acceleration. Um, so, in this lesson, we are talking about the analogs to mass and force as well. Force will actually be later. Even though mass is not like a linear thing, mass works differently when it's being rotated. Um, so we don't talk about mass in rotations. We talk about rotational inertia. So if you could pause the video and make your note card here. The front's going to be rotational inertia. The variable for this is I. Oops. If you want to add that to your note card, so go ahead and pause the video, write this down, and then we'll talk about it. Okay, so again, we know inertia is the amount of an object's resistance to motion. And again, rotational motion, again, it's not just the mass that matters. It's actually how far away the object is from the axis of rotation. Now, this only works for certain objects. So on the AP test, if it's not a solid object, and we're going to talk about this in the lesson, um, the rotational inertia is going to be different because the mass is distributed differently. Imagine like a hula hoop versus a plate. Even though they're both circles, the mass is distributed differently, and so they won't have the same rotational inertia. So there are formulas for these different objects. They'll provide them in the question if you absolutely have to use them. And the units for rotational inertia, hey, we shouldn't be able to do this now. I should be able to do this immediately because it's mass and radius. It's kilograms for mass and m squared for r squared, right? Meter squared. So kgm squared is rotational inertia. Okay, just last slide we're going to do here. So the true formula is I equals, and sorry guys, I got too lazy. I was gonna make this I a better looking I. Whenever you see that in your notes, it's I. I will clarify that. It looks like L. Anywho, the true formula that applies to all rotating shapes is that rotational inertia equals the sum of all of the individual, like itty bitty, insignificantly small masses and how far away they are from the center. If we chopped up the object into an infinite number of pieces and added together the masses times the radius, the distance they are from the center squared, we'd get the rotational inertia. That requires some calculus. Dealing with infinity is calculus. So in this class, we just have the basic formulas. Obviously, we're not doing calculus. What this means is rotational inertia is additive. So if the object has multiple pieces, we can add together their separate inertias to get the sum inertia for the whole. That sounds more complicated than it is. It's really not that bad when you're doing a problem. So, thinking about proportionality, how m and r relate to inertia. Well, if we have more mass, what's going to happen to the rotational inertia? Well, we're going to have more, meaning it's going to be more resistant to motion, i.e., it's going to be more difficult to rotate it in this case. But more distance from the axis, so the further away I am from the center, what does that mean for inertia as well? Also more inertia. So what this means is a very small object can be very hard to rotate if that mass is super far away from the center. And again, hopefully this is something that you can understand as something that you've experienced in your real life. If you're swinging something around and it's got a very small radius, it's not too bad. Get that thing super far away from you and you're like, whoa, trying to get it all the way around. So because of that, the rotational inertia depends on the axis. If we move that axis, I is going to change. So you got to be really careful about where the axis is. So for example, here in this question, we're going to do this tomorrow or, Monday, whatever. My axis is here in each case. If in the last case, if I moved this axis to be here, and that's where I was rotating it through, the inertia would be very different. So we'll talk more about that tomorrow, though. Monday, whatever.